Well, thank you, Wayne, and I'd just like to say, as I always do, thank you to the Society for inviting me to talk tonight. So what I'm going to be talking about tonight, I'm just taking this off so I'm a bit more comfortable while I'm sitting down, is solar power space satellites, as you can see on the slide there, the concept and plausibility. Now, I'll start off with a caveat that I'm not an expert in solar power space satellites. I'm just a space very eager and interested in space, and I talk about various topics. Now, solar power space satellites, my first introduction to this was when I was in high school, believe it or not, and I was one of those students who used to sit in the library and read things, and I heard about solar power space satellites, and I wrote a letter to NASA, and I said that I was researching solar power space satellites. So in those days, NASA had some money, and they sent back to me, believe it or not, almost a metre of NASA books on the various projects that they were working on at the time. And some of the books dated 1978, so that's when I sent the letter, was on solar power space satellites. So that's the background. Let's get into the talk. Now, I'm going to talk about a couple of things here. Solar power space satellites, you've probably all heard of various announcements that are happening right at the moment, and the concept of what it is. The picture behind me gives you a very brief and simple explanation of solar power satellites. You have energy from the sun. Rather than collecting the energy on planet Earth, solar panels, it's collected via a satellite one way or the other in one place or another in space, and we'll go through those, and then that energy is beamed one way or another down to planet Earth, and you can see that in that diagram. We'll go through all of the options. So, concept. Space-based solar power is a concept wherein a large orbital photovoltaic array converts photons directly into electricity, which is then converted into microwaves, or lasers, that are beamed to collectors on the Earth's surface, where they are converted into electricity and fed into the grid. There are substantial hurdles to operationalise and commercialise this concept. Various solar power space satellite proposals have been researched since the 1970s, but it's not yet technologically feasible or cost efficient, not yet. But research is ongoing by governments and companies in Japan, China, Russia, India, the United Kingdom, the United States, Australia, etc., to try and make this concept commercial. SPSS represents a virtually carbon-free post-launch power source. Now I say post-launch because there's a lot of tonnage to get into orbit. Today, geopolitical and new energy imperatives are the driving factors behind solar power space satellites. Global power demand. According to the Energy Information Agency, EIA, the demand for power globally will be over 5,000 gigawatts per year by 2050, of which 50% must be from renewables. Traditional solar power, wind power and battery technology have fundamental limits, including land demands, that constrain the ability for these to meet the forecast power demands. Fusion power is another great concept, but the limiting factor will be the availability of deuterium and tritium. While deuterium is abundant in the sea, tritium is produced as a byproduct of CANDU type fission reactors and is much more difficult to obtain. The current global inventory of tritium is around 20 kilograms. The future of fusion power will depend on the successful development of tritium breeding blankets and the ability to produce and recycle tritium from within the fusion reaction. So fusion is a great idea. Apart from the obvious technical problems, source of some of the raw materials is a major problem. This shows you, this complex slide shows you some of the concepts of solar power space satellites. I won't go through the details of this, because I've got a couple of tables coming up which will go through the details on where we are at the moment and where NASA thinks we might be in a couple of years. There are a number of advantages of solar power space satellites once we get the technology up and running and costs down. First of all, you can link the concept to putting data centres into space, and Elon Musk has made a lot of commentary about that in the last 12 months, and use direct solar energy. The US startup company StarCloud is investigating this possibility, as is, of course, Elon Musk. In November 2025, StarCloud sent a refrigerator-sized satellite into orbit containing NVIDIA GPU chips, that's graphic chips, to test this concept. Google, in November 2025, unveiled plans to launch test satellites by early 2027. We should check and see whether they're still on schedule, as part of the Suncatcher project. In addition, Elon Musk and Starlink announced also in November 2025 that Starlink could be used to launch data centres in, quote, 2026. But a lot of Elon Musk's timetables tend to slip a fair bit. The University of Arizona believes this could be a commercial within a decade, and Amazon founder Jeff Bezos believes this could take 2 decades to bring to commercial reality. So we're still some way off. Satellite-based data centres would reduce the need for land on Earth for solar power and reduce the extensive water demands of data centres. Now, just in the last month or two in Australia, that's become headline news, the requirement for water. It's been headline news in parts of the United States for some time. Reduced launch costs could improve the economics of space-based data centres to be comparable to Earth-based data centres. Some of the numbers I'll talk about in tables coming up, they are dramatic improvements we require. And also, of course, it is solar noon wherever solar power space satellites will be located. That's to say they'll be in sun all the time. And they can generate electricity 99% of the time. Earth-based solar panels typically only generate power for 29% of the time, depending on their location. So that's an average, 29%. An SPSS with directional beam could direct their beam to various Earth-collecting arrays, and the concept there is you have your solar array on planet Earth. It's only generating electricity 29% of the time, so a satellite will just redirect its beam so that for a few more hours a day you can generate electricity. Doesn't rely on water sources, almost zero hazarded waste. Now, again, that is after launch. The space-based solar panels will not have obstructions such as atmosphere and dust to worry about. The frequency of the beam from the satellite to planet Earth will be such that the interference with the atmosphere will be minimised. And also, with the stagnation of new uranium nuclear fission power plant construction and continuing uncertainty about the viability of fusion or carbon capture, there is no practical way to achieve the high levels of baseload power outside of certain geographically constrained circumstances. Now, I did mention the uranium fission. I think, this is a separate topic, that thorium fission is the way to go. So I'm just waiting for more announcements on that line. As the world is rapidly moving away from coal-based load power generation, a range of alternative energy sources is needed. Space-based solar power is one option, even if it is a longer-term solution. So they're the advantages. What are the disadvantages? There are a few. Computer chips, including the GPU, the graphic chips for data centres, will be subject to high levels of radiation and extreme temperatures, as well as the risk of being hit by space debris. And this is, of course, also the same with other commercial satellites, and in some instances is part of the reason for limited life for these satellites. the cost of launching thousands of tons of material into low Earth orbit and then to GEO for a gigawatt class power station is at the moment very large. There's the impact of what's known as airy disk spreading, and the problem there is beaming anything through the atmosphere. The beam tends to diverge as it goes through not only the atoms in the atmosphere but dust and everything else that's up there. A 1 kilometre disk in GEO transmitting at 2.5 gigahertz needs a 10 kilometre diameter collecting dish on planet Earth. Now here's a problem. A beam angle of 7.2, remember 7.2 arc seconds from GEO, is required to stay within the 1 kilometre diameter receiving array, 7.2. At the moment, the most advanced current wireless beam spreads at 54 arc seconds. So there's a lot of technology enhancement required there to make the beam really directional. The space environment is hostile, as we know. There's a large cost and size on the Earth of the receiving array. These are all disadvantages. The energy losses from GEO collectors to Earth power distribution. There are the issues of waste heat disposal in space. What do you do with the heat that you are generating? Space is not a very, very good conductor of energy, so somehow you have to radiate that energy away. The decommissioning costs and process, we're talking about massive structures in space. After they become non-commercial, hit the end of their life, someone's got to invest the funds to pull those apart and put them somewhere, either back on Earth, burn up, or towards the sun, or just move them out of the way. Very large cost. Also, there's the issue of autonomous operations in space. Okay, we've got a number of satellites up there that work very well for a long period of time, but in this case we're talking about very large structures that have to work autonomously, a completely different ballgame. There is the issue with space debris. If you have a very large structure up there, it is going to get hit. Just ask the International Space Station at the moment. There are technology challenges, and also, of course, there's, as always, the potential to interfere with high-resolution astronomy observations. Okay, so let's just look at some of these challenges in a little bit more detail. Excuse me. First of all, the European Space Agency has identified the following technology bottlenecks. First of all, as I said, very large structures, the manufacturing and the deployment, getting them up there, putting them together, getting them to work. Construction, power generation and onboard energy conversion, talking about high voltages, we need efficient solar to electric and electric to microwave or laser conversions. Thermal systems, the need for efficient large radiators and distributed thermal subsystems. So this is all managing the heat that you're generating. You need to have efficient wireless power transmission systems, whether they be laser or microwave. You need to be able to control them, to focus them, to point them, and to continually change that over time. You also need the microwave or laser, depending how you're generating the energy to Earth, to electric conversion on planet Earth. Also, the various control structures, etc., up in space, especially if you're managing a constellation of satellites to generate this electricity. It becomes very, very complex. Number two, technical. First of all, the scale of the operations. I mentioned this several times before. Industry needs to reach the capability to deploy thousands of satellites per year to reach the capabilities needed to launch and assemble these satellites. Now, Elon Musk can do that at the moment with his Starlink. We're talking about a completely different game here, different size. There's the coordination efforts to deploy these satellite components. And also, without robust in-space servicing, assembly and manufacture, it's called ISAM, The assembly, maintain and disposal phases will be slow and expensive. Automated options for space-based assembly are well beyond current capabilities. Space beaming. Apart from any US defence capabilities not known publicly, energy beaming is currently orders of magnitude below the requirements. DARPA at the moment is currently developing a program called POWER, Persistent Optical Wireless Energy Relay, which is power beaming. Whether the Department of Defence has the ability to beam energy from space to Earth, we don't know, but on the civilian side, don't have the capability yet. Photovoltaic cells are very expensive and heavy. We need lighter and cheaper solar cell technology. Now that's happening right at the moment. There's been a number of very good announcements along that line. Also, the current photovoltaic technology is based on a few hundred volts. It needs to be enhanced to manage many hundreds of volts. Not there yet. And with power beaming coming from satellite to planet Earth, if you use low frequency, you need a large Earth-based collecting array, very large. If you use a high frequency, then you have a high energy loss in the atmosphere. So you need to have that balance. And also, of course, as we have very large structures operating in space, there's the potential for each of these structures to distort while they're in space as well. Now, if you don't have people up there, in the International Space Station, if it was to twist or you had problems, you actually have people there who can fix it. There's no one at these SPSS. A couple of regulatory issues to get through. SPSS will be unable to avoid collisions with space objects, small meteors, etc. And then, of course, there's the threat of cascading debris. Large structures, once they start falling apart, and if you've got hundreds or thousands of them up there, the models at the moment assume the final disposal of these satellites will be in some graveyard orbit. We're talking about hundreds or thousands going into a graveyard orbit. Again, we're talking about a different scale of events. Radio spectrum allocation. SVSS beaming may interfere with other low Earth orbit systems. Research is needed in this topic. Orbital slot allocation, that's set by the ITU. The slots are already becoming contested. If you want to put a couple of thousand more satellites up there, large, then you start to have a problem. And also, of course, cyber security, especially for any automated systems up there. A couple of legal things. Now I'm going to run through the various declarations just very quickly, or treaties and declarations that the solar power space satellites need to comply with. There's a lot of them. Very quickly, 1967 Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space. 1968 Agreement on the Rescue of Astronauts, Return of Astronauts and the Return of Objects Launched into Outer Space. 1972 Convention on International Liability for Damage Caused by Space Objects. Look, I won't read them all out. There's about 10 or 15 of them in this list here. So, as with everything to do with space, there's a lot of legal requirements. Point number 5 I've got here is a commercial issue. The scale of the system may limit private investment involvement. Now, this is in the final product. There's a whole lot of companies at the moment investing in developing the technology, which is different to investing in building the final product. Launch capacity required. 104 launches per year during launch and assembly phase. Current global launch capacity is 186 launches per year. For example, Starship will need to expand its launch capacity by 5 to 10 times and dedicate all of this just to these solar power space satellites. So we don't have the launch capacity at the moment. So what have we done so far on this topic globally? I've got a list of many things that have happened since 1941. Again, because of time, I don't think I'll read all of these out, but I'll give you just a couple of ideas. First of all, Isaac Asimov, one of my heroes, published a science fiction story, Reason, in which a space station transmitting energy collected from the sun to various planets was published. So the idea started at least in 1941. In 1968, Peter Glasser introduced the concept of solar power satellite system. So the real thing started in 1968. Then you had Japan, United States, various universities conducting studies. NASA's done a whole lot of studies, and I've already shown you the 1978 study that they put out. There are various testimonies to the United States House of Representatives, such as in the year 2000, along this line. The European Union from 2003, if not earlier, has been studying this concept, and it has a fairly advanced program underway at the moment. Even the United States Pentagon in 2007, their National Security Space Office issued a report stating they intend to collect solar energy from space for use on Earth. This is in 2007. They said a demo plant, a demo satellite, would cost $10 billion and produce 10 megawatts and become operational in 10 years. So that was up to 2017. Now that was just a concept. Obviously it didn't happen, but that's what they were thinking at the time. MIT held a workshop in 2007. India has their space research organisation. They looked at this in 2010. The list just goes on. There was, again, another NASA report in 2017. Kyushu University in Japan, 2019. China, 2019. In 2020, the US Naval Research Lab launched a couple of test satellites. So that was 6 years ago. US Air Force got involved in 2020, do some experimentation. 2021, Caltech. 2022, United Kingdom. 2022, the Space Energy Initiative in the United Kingdom announced plans to launch the first power station in space during the mid-2040s to provide, quote, 30% of the UK's electricity demands after the 2040s. So the UK is thinking seriously about it. Whether it'll work, we've yet to see. In 2022, the ESA, Europe, proposed a program called Solaris to operate solar power satellites from 2030. 2023, Caltech was involved again, looking at the ability to beam power as a concept. So that's, I've got 2 pages of one-liners on the various research projects. So there's a lot of organisations and governments looking at the concept. We have a long way to go yet. Looking at laser beam rather than microwave energy from space, NASA's been working on this since the 1980s. We'll see how productive that becomes, but they've spent a lot of time on this so far. I wouldn't be surprised if the US Department of Defense is actually a lot further along this track than we expect, because they have some very advanced weaponry based on lasers. So they are probably able to do this already. Now, one of the issues is if you have a very large solar panel in space and you want to direct it at certain places on planet Earth, you're not going to move this thing, which is several kilometres in size, to redirect your beam. So there's work going on at the moment on 360-degree power transmission. This was pioneered by a company called Space Solar, or according to my research it was, and their Harrier system. This allows energy beams to be directed in any direction without moving parts. Typically uses helical antennas and electronic steering, which allows you to direct the beam they say anywhere, obviously not anywhere, but over a large part of planet Earth. Also, this can serve as an emergency power for disaster relief. If you could imagine that power is out in a major part of, let's just pick a country, India, or maybe somewhere in Africa, you can move solar panels into that part of the world fairly quickly and then get the satellite to direct its beam to your solar panels and get emergency power into that community. So that's one of the things they're looking at as well. Okay. Current studies. So I talked about the past. Where are we at the moment on this? The UK Space Agency is currently supporting a number of initiatives including in-orbit manufacturing and assembly, debris mitigation, power beaming from space, and mission system studies. So they're looking at most of the facets of getting satellites up there, commissioning them, using them, and what to do with them at the end of their life. China, as it always does, has announced in 2025 that it plans to build a 1 kilometre wide array in geostationary orbit, that's 36,000 kilometres up, and achieve a 10-fold increase in efficiency compared to Earth-based solar power. The Chinese Academy of Engineering has stated they're working on this now. The European Space Agency is still active. They have an ongoing review of solar power satellites and hold seminars and workshops to investigate the challenges and required developments. NASA has held and continues to hold a number of workshops on solar power satellites. Australia, company Extraterrestrial Power, has developed a mass-manufactured solar cell that is, or they claim to be, 10% the cost of other cells. Now, there's a lot of research in this at the moment by various companies for various applications. So this company, Extraterrestrial Power, believe they have the cost down to 10% of other solar power cells. It's based on thin cell technology that can survive space conditions, which is interesting. It has been demonstrated already on Caltech's solar power experiment in 2023, and the company also claims to be gearing up for actual manufacture. That's been funded by the Australian Space Agency, so let's just see where that program goes. Australian-based Solar Space Technologies, so they plan to launch a satellite by 2027. I think they might be optimistic, but at least they're working along that path. Japan-based Rated Power have a project called OHI-SMA, Ohi-sama, I presume you pronounce that. It's a low Earth orbit-based satellite system. Their initial aim is to launch a 180 kilogram satellite into a 400 kilometre orbit and just to test the beaming of energy to Earth. Now, you may also have read people testing beaming from one hilltop to another on planet Earth as well. That may be for Earth-based applications, but of course once they get that to work, that technology can also be used one way or another for beaming from satellites to Earth. Japan Aerospace Exploration Agency in 2015 stated that solar power space satellites could be a reality within 25 years, so that takes them to 2040. So that's Japan's timeline. Let's just see whether that's realistic or not. It sort of is in the ballpark. How are we going for time? 8 o'clock. There's a whole lot of other work happening with the University of Glasgow, Russia, other countries, all looking at trying to commercialise this concept. This map shows you the countries that are working on solar power space satellites at the moment. So it's fairly widespread, Right, so let's do a comparison of this technology compared to ground-based solar power. And this will be based on more current work done by NASA. NASA performed a purely technical and cost analysis of space versus ground-based solar power generation. This review did not consider the technical, legal or regulatory aspects. The analysis compared solar power satellites in geostationary orbit to a concentrating solar power system on the ground. So GEO compared to what we're doing today. They assume the power plant is 1 gigawatt in size. Their conclusion, even though the solar power satellite concept has a higher end-to-end efficiency, the combined space and ground collector infrastructure is about the same as a comparable Earth-based system based purely on cost. Based purely on cost, there are a couple of caveats on that. I'll just go to slide 14 because this slide and slide 15 coming up shows you the total efficiency of the solar power satellite system. So obviously you start off with sunlight, 100%, the starting point. There are various processes and technologies required to turn that sunlight energy into usable energy on planet Earth. This slide gets you roughly halfway there. The last slide here is atmospheric attenuation to microwave radiation, so how much energy you lose basically coming through the atmosphere. So that's 90% loss there. If we go right down to the bottom, this system is roughly 15% energy efficient. That's solar-based electricity, from the satellite. 15% efficiency. Also, you need a fair bit of infrastructure. If you look at that number 15.15, the total area that you need is that's in square kilometres, 15 square kilometres for your 1 gigawatt power plant. Now that's your solar collector array up in space and your receiving antenna down on planet Earth. Now if you include the so-called keep out zone, so that's the exclusion zone around your collector on planet Earth, you're actually talking about a total area of 34 square kilometres. So these are not small installations. Solar panel technologies are becoming increasingly efficient, with 50% efficiency now possible. The size of the space segment is large regardless of solar panel design, and these space efficiencies have no impact on the size of the ground-based infrastructure. Now if we look at the equivalent solar panels just on planet Earth, so we're doing a comparison of space compared to what we do today. We have the concentrating power efficiency of the system on the Earth system here. Now, this runs down to 43% efficiency, but then if you have two-axis tracking, you can bump that up again. And then you come down, if you consider all of the factors in generating the electricity, the total efficiency is 4.8% for land-based solar panel arrays, 4.8%. Now that's NASA's study. The power collecting tower on ground has a low efficiency at around 14%. It is possible to increase this efficiency of the power tower on planet Earth from 14 to 44% if a switch is made from molten salt as within the energy system to steam turbine. If this efficiency is possible, the collection area will fall from 15.15, that's the number I showed you before, to 4.82 square kilometres for the 1 gig power system. So we're talking here about massive changes to technology which NASA thinks is possible. I've got a few more slides from NASA here. I don't think I'll go through this one in detail because of time, but I'll read through the conclusions, if you like, from NASA. The solar power space satellite concept has both a large space infrastructure segment and a large ground infrastructure segment that is about equal to the total constructed systems area of a ground-based system. The ground-based system uses reflectors and heat engine to produce power and therefore avoids the inefficiencies of photovoltaic conversion of light to electricity. In addition to the launch cost, there is a cost of in-orbit construction, maintenance and repair for solar power space satellites against the ground construction, maintenance and repair of those systems. Rough order of magnitude estimates indicate that the solar power satellite concept launch cost was not the only problem that precludes it from being a practical system today. There are other applications for the solar power concepts that should be investigated. These include further research into small, low to mid-Earth orbiting solar power constellations that could supply airships and ground stations for remote areas, military and disaster relief, as I mentioned before, applications. Solar power satellite technology will continue to be of interest to NASA, including further development of photovoltaic arrays, microwave and laser transmission, and power storage and conversion technologies for space applications. So what they're saying here is let's keep on doing the research into these technologies because we can use them elsewhere within NASA. These space applications of interest include all government and commercial satellite systems, robotics, science and exploration missions, and future human missions beyond low Earth orbit to the Moon, asteroids, and Mars. Now, NASA put Mars into their study there, but if you remember one of the talks I gave a little while ago, I personally don't think man's going to get to Mars anytime soon for a number of reasons. Okay, so there's also a concept of if you're going to put a large structure up in space and NASA wants to continue putting men into space, why don't we just combine them and wrap the next space station in solar panels and then beam the energy down to our planet Earth? So that's a concept. A large number of mass-produced modular photovoltaic elements, they would self-assemble into the structure. The location suggested is Lagrange point 1 between Earth and the Moon. Design, this design is for a toroidal structure, as you can see. Manufacture on the Moon. Now, I have a bit of a problem with the concept of manufacturing on the Moon. The materials might be there, but if you have a look at the size of the industrial plants on planet Earth, it's not easy to turn materials into usable products. Anyhow, that's another topic. You need elements sent to orbit using a mass driver. Okay, from the Moon, assuming you manufacture the items, that's a logical place to get them to L1 using the mass driver. Then you have to assemble all the products, all the items into the final product. And bear in mind that if you're launching anything from planet Earth, the launch costs could become prohibitive. So what did NASA say in 2024? So they keep on working on this. There's a growing global interest in solar-based, they've changed the acronym, but it's basically space-based power. Experts in both the aerospace and energy sectors are debating the benefits of solar-powered space satellites as more organisations globally begin their technology development programs. Proponents claim that technology could deliver large amounts of electricity at competitive prices and with fewer greenhouse gas emissions than terrestrial renewable electricity technologies, while accelerating development of the space economy. Skeptics say that this concept has no clear development path and would divert billions of dollars from known terrestrial solutions while damaging the environment. Damaging the environment, as I said several times, you've got to get these items up into space. The damage from the launches would be fairly horrific. While it is generally understood that space-based solar power is cost prohibitive and technically infeasible today, the study they did in 2024 assesses what could happen in 2050 if we continue investigating this. NASA assessed two representative designs, the innovative heliostat swarm, which is, they call it RD1, Representative Design 1, and a mature planar array, just standard solar panels, which they called RD2. And I think that one of their engineers must have been a Star Wars fan or something, R2-D2. Okay, so RD1 generates power 99% of the time, and RD2 generates power 60% of the year, just because of the design limitations. The objective was to deliver 2 gigawatts of power to the electricity grid. There are 5 RD2 systems needed to deliver roughly the same amount of power as one RD1 system. So they're looking at what's the mass of sending these systems up into space. For RD1, which was the heliostat swarm structure, the solar panel area is 11.5 square kilometres, and it's just under 20 square kilometres for RD2. Launching 20 square kilometres of material into space. Slightly expensive and time consuming. The RD1 solar panel, that's the heliostat swarm, area is more than 3,000 times and 27 times greater than the International Space Station and the Starlink constellation respectively. The mass is just under 6 million kilograms, 6,000 tonnes, and 10 million kilograms for the RD2 system. A lot of mass to launch into space. The timeline. This is again NASA's 2024 concept. They looked at building the systems on planet Earth and then launching them in the 2030s to low Earth orbit, then transferred to and assembled in geostationary orbit sometime in the 2040s. So the system would exist 10 years, whatever, in low Earth orbit in parts, however you want to define that, and then push them to geostationary orbit sometime later. Operate from 2050 to 2080, transmitting energy to Earth. Then you need to maintain these satellites between 2060 and 2080 as they start to degrade. So somehow you need to get robots to these satellites to maintain them. And then you have to dispose of them somehow. So it's a lot of mass to either put into a graveyard orbit or do something else with them. And that takes a little bit of energy. Now, just keeping an eye on the time here as well. If I just skip to slide 26, the cost competitiveness can be achieved by varying multiple assumptions at the same time to provide a combination of cost and capability improvements beyond the advances already assumed in their baseline assessment. The favourable combination reduces the levelised cost of electricity, LCOE, to, remember this number, $0.03 per kilowatt to $0.08 per kilowatt, depending on the system you're using. And they are competitive with terrestrial alternatives. Now that's assuming you do a lot of enhancements. Key input parameters for multiple variable sensitivity analysis. Okay, NASA's got one of their little terminologies there. You can read this. What this is saying is the baseline study from 2024, which they basically said is not going to work commercially. And they said, if you want to make it commercial, this on the right-hand column is basically what you have to do to make the system commercial. So you've got to drop the cost of the launch cost by half. You need to increase the solar cell efficiency from 35% to 50%. You need to extend the life of your hardware from 10 years to 15 years plus. You need to drop the cost of your hardware significantly, and you need to, it says here, manufacturing learning curves. What that basically means is we don't know how to do it yet, and we've got to learn very quickly how to do it. So a lot of things need to change to make this economic. And now, unfortunately, we've got something overriding the text here. I'm not sure how it comes up for the people online. But the levelised cost of electricity, that's the second bottom line here. In the base case, it's between 0.61 and 1.59. You've got to get that down to Earth solar power equivalent, which is 0.04 to 0.08. So you can see a massive drop in cost is required to make this commercial. The total cost for each of the systems, remember we're talking about RD1 and RD2, and they're the two different design systems for the solar panels in space. RD1, the heliostats, $276 billion, and for RD2, $434 billion. Now, unless this is in the military budget, the United States hasn't got the other money to fund that at the moment. And of course, NASA's had rather devastating budget cuts, so they're not going to be able to find $400 billion in the short term. The combined in-orbit mass of the 5 RD2 satellites for 2 gigawatts of power is, I think I said this before, nearly twice that of the alternate system that they looked at. 1,000 metric tons versus 585 metric tons. Imagine launching 1,000 metric tons into space. The primary mass-based cost drivers are related to the launch and disposal. Greenhouse gas emissions on launch. The baseline life cycle greenhouse gas emission intensity is 26 grams of carbon dioxide equivalent per kilowatt hour. Now this is mainly a launch cost. So these, when people say we're going to put these into space because it's clean energy, it's only clean once you get it there. It's very dirty to get it up into orbit. I'll just skip the next few bits of the NASA study because it talks about launch schedule and a few other things. The hardware life, we talked before about the current estimate is 10 years hardware life. So that's actually interesting. You take that launch mass of 1,000 metric tons and it only lasts for 10 years. So you have to launch the equivalent of 100 metric tons every year, equivalent, like if you want to amortize it. So how to make it more commercially competitive, according to NASA 2024. They say that even if you were able to reduce the launch cost to zero, it may not be cost competitive. They do acknowledge that launch costs have decreased by 36% over the 10 years to 2024, and Elon Musk, as we know, is working very hard to cut those even further. Solar cell efficiency, currently around 33%. That's NASA's number for 2024. State-of-the-art technical efficiency is actually 70%. Now, I read that as laboratory efficiency, 70%, compared to 33% commercial, let's say, solar panels. Commercial costs for in-space servicing, assembly and manufacturing suggests that $100 million for that part of the project may be possible in 15 years. Learning curve, we talked about the learning curve on that previous slide. 80% possibility leading to cheaper costs overall if we can learn how to do it. The movement of products from low Earth orbit to geostationary, that has been effective for over a decade. The technology is not a big problem, but you are moving a lot more, so you want to be able to do it cheaper now. We need more advanced materials to reduce the weight. NASA is working on a number of projects, their lightweight materials and structures project and super lightweight aerospace composites for their own needs. And of course, once they get those materials for their own needs, they can be used for just about anything, including these satellites. And also, just the concept of managing a constellation of satellites in either low or medium Earth orbit. It's not just a simple thing. NASA believes that cost competitiveness may be achieved through a favourable, I think we just read as at this stage we think unlikely, combination of cost and performance improvements related to launch and manufacturing beyond the advancements assumed in the baseline assessment. So a lot more needs to happen. Their baseline is that maybe in a 30-year time frame, solar power space satellites could be added to the range of power sources for planet Earth. So, solar power space satellites is an interesting concept to generate and distribute clean, after launch issues are considered, energy. The space system will be very large and various technical and regulatory issues need to be worked through. But in a 30-year time frame, SPSS could be added to the range of power sources for Earth. In addition, the capabilities created through the research and manufacturing effort could be used for other applications and indeed to support a wider range of space activities. I have to say that my personal view is I think that thorium fission is the way to go. For those with a long memory like myself, the United Kingdom used to call those fast breeder reactors. The United States told them to stop researching that for the unusual reason that there was no waste products from thorium fission, and the problem with no waste products is there's no plutonium, and America wanted plutonium. So that's why England stopped researching it. China has taken up where the UK left off, and I think you'll find a lot of thorium-based fission reactors being built by China soon. But this does still remain as a longer-term concept. So, that's it. Thank you for listening to my talk.
What we'll do is we'll take questions from the floor and then we'll go to the...
Yep.
So we'll try and get a couple done and then... Okay, so we've got any questions here?
Are you able to put the people that have logged in up there?
Sorry?
Are you able to put the people that have logged in up there?
Oh, Wayne, I want to show the people logged in.
You have to start your screen. Not too much of this.
We're just bringing everyone up on the screen.
They don't log out.
Don't log out. There's 13 people on at the moment. Sorry, I can't move I can't control the mouse at the moment. I don't even know where it is. Maybe if you just kill the presentation. The presentation does do this. Okay. No, you have to come over and look, please. I'm not doing all the work things. Okay. It's just a break. Okay, I think we had a question.
Considering there's space satellites and fusion, which one's easier to achieve at the moment? Do you have any idea about that?
Okay, fusion. That's an interesting topic. My view is that fusion is a long way in the future.
It's further than the space satellites?
Yeah, I think so. That's my view. The people who are doing the research in fusion say it's all 5 or 10 years down the track. There's a lot of issues with the internal wearing away of the fusion reactor itself, the sourcing of the tritium, which I said is only 20 kilograms on planet Earth in total, and generating on a sustainable basis more energy than you're putting in to the system. Whenever you hear people say, "Oh, we generated, whatever X watts of energy," that normally is not greater, or it's equivalent to the amount of energy you're putting into the system. So you're not generating net energy at this stage. I think there's a lot of work required on with that. So. I would probably put this ahead of fusion, but I think it's line ball. I think it's line ball.
Could this be looked in as far as using the moon as the satellite and deflect? Because the sun deflects light by the moon, and we see it every night, no matter where we are in the world. That the conversion on the moon can be converted to microwaves from the moon.
When I was, because of time, when I was flicking through these notes, one of the proposals is to actually put a band across the equator of the moon to reflect the energy off the moon. Now, of course, you can't do that. There's a whole lot of treaties that say you can't do that, and a few other issues as well. You're talking about massive manufacturing plants located on the moon, and that won't happen. So just someone with a concept. Look, physics will say yes, that'll work. The treaties and economics says that it won't work.
I think also that the beam accuracy from that distance
Yeah.
is not practical.
Yeah. That comes up with those arc second numbers that I was talking about before. Yeah. Any more questions from here before we go to the floor? If you want to go back to see what's in the chat. Nothing there? That's all I can see. Yeah. Well, obviously there's some problem, but I can't fix it. Yeah. Okie doke. Well, on that, I think I'll say thank you, everyone. Yes, you can see it's a topic that I've been researching for a few years. Good.